Hello, and a very warm welcome to the Sleepy Scientist. I'm so glad you're here tonight. Together we're going to wander into one of the strangest, most wonderful claims in all of physics. That a single quantum particle can be in two places at once. First though, a brief and honest word. You've probably noticed there are no ads on these videos, so nothing will break the quiet tonight. Keeping it that way does take a little help though, and the best way to lend it is the ebook. If you have a spare minute, and only if you do, pause here and take a look. There's a QR code on screen throughout, and a link down in the description across to the website, thesleepyscientist.com. It's an unhurried, patient guide to quantum physics. The ideas behind these videos given a little more room to breathe, with the full narrated audiobook alongside. Honestly, a quiet look really is the most helpful thing you can do to keep these videos coming. That's all I'll ask tonight, and I ask it warmly. Thank you. Now before we begin, let me know where in the world you're listening from, and what time it is for you. I always enjoy seeing how far these quiet little journeys travel, while the rest of the world is busy pretending to be sensible. It's a claim that really should come with a small warning label. In ordinary life, things simply aren't allowed to behave this way. A cup is on the table or it isn't. A planet is on one side of its orbit or the other. You're either in bed listening to this or somewhere else insisting you aren't tired yet. But at the smallest scales, reality follows different rules. Electrons, photons and atoms can be described by states that hold more than one possible position or path at once before anything is measured. They aren't tiny balls hiding in one secret place. Their possibilities can spread, overlap, and interfere. And when we look carefully enough, those possibilities leave real patterns behind in real experiments. So tonight we'll move gently from the familiar world of ordinary objects into the stranger world of matter waves, superposition, and the double slit experiment, and towards the delicate reason this weirdness usually disappears long before it reaches the scale of cups, chairs, cats, and people. So get comfortable. Let the day soften a little around the edges, and picture a single tiny particle moving towards two possible paths. In the world we know, it should choose one. In the quantum world, that assumption is exactly where the mystery begins. In ordinary life, being in one place at a time feels less like a scientific rule and more like common sense. A cup sits on a table. A chair rests in the corner. A person cannot walk through one doorway while also walking through another doorway on the opposite side of the room, unless something has gone very wrong with the doorway, the person, or the story being told. This is the world our senses are built for. It is a world of definite locations, solid objects, steady surfaces, and paths that can be traced from one moment to the next. If a football crosses a field, it does not blur into every possible route at once. It follows a path. If a stone falls from a cliff, it does not explore a polite selection of alternative cliffs on the way down. It falls in one direction, under gravity, with a motion that can be described extremely well. For centuries, this was the heart of physics. Isaac Newton gave the world a deep and powerful description of motion. In Newton's classical mechanics, an object has a position. It has a velocity. It has a mass. Forces act on it, and those forces change its motion. If enough information is known about the object and the forces around it, its future path can be predicted. This picture is not wrong in the world where it belongs. It is one of the most successful ideas in the history of science. Newton's laws describe falling apples, flying cannonballs, orbiting moons, tides, pendulums, bridges, engines, and spacecraft with remarkable accuracy. They are so good that even today, engineers and astronomers still use Newtonian physics whenever the speeds are not too close to the speed of light and the objects are not too small. In this classical picture, a particle is like a tiny object with a definite location. A grain of sand sits somewhere. A planet moves somewhere. Even if we do not know exactly where something is, classical physics assumes that the thing itself still has a definite position. The uncertainty belongs to us, not to nature. The object is not confused. We are. Imagine closing your eyes while someone places a coin under one of two cups. You do not know which cup hides the coin, but you naturally assume the coin is under one cup or the other. It is not truly under both. Your uncertainty is only a lack of information. Lift the cup and the answer is revealed. This feels obvious, and in everyday life it usually is. But the quantum world does not always behave like a hidden coin under a cup. At the scale of atoms, electrons, photons, and other tiny systems, the question of where something is becomes much more subtle. The particle is not always best described as a miniature ball sitting in one secret place, waiting for us to discover it. Instead, quantum theory describes it using a quantum state, and that state can spread across different possibilities. This is where ordinary intuition begins to wobble slightly. Not collapse dramatically, perhaps. Just wobble, like a table with one short leg in a quiet laboratory. The reason we do not normally notice this strangeness is scale. Everyday objects are enormous compared with quantum particles. A dust grain may seem tiny, but it contains an immense number of atoms. A bacterium is microscopic, yet it is still a vast structure compared with a single electron. A human body is not merely large by quantum standards. It is an entire weather system of molecules, heat, motion, light, electrical activity, and constant interaction with the surroundings. An electron is far smaller than an atom. An atom itself is roughly a 10 billionth of a meter across, depending on the atom and how it is measured. The nucleus at the center is roughly 100,000 times smaller than the atom as a whole. These sizes are so far below ordinary experience that our everyday mental pictures begin to fail. We can imagine tiny balls, tiny orbits, and tiny paths, but those pictures are borrowed from the large world. Nature is not required to use them. Large objects also interact constantly with their environments. A chair in a room is being struck by air molecules. It is absorbing and emitting thermal radiation. Light is bouncing from it into your eyes. Its atoms are vibrating. Its surface is exchanging information with the world around it all the time. These interactions make the chair behave in an overwhelmingly classical way. Its quantum possibilities are not absent at the deepest level, but they are hidden so thoroughly that the chair has no practical chance of showing up as a visible superposition in two different corners of the room. A quantum particle can be different, because it can sometimes be isolated. A photon travelling through a carefully arranged experiment or an electron passing through a narrow opening can avoid enough environmental disturbance for its quantum nature to remain visible. Under those conditions, it may not behave like a little pellet flying along one fixed route. It may behave more like a spread-out possibility, one that can pass through more than one available path and later produce effects that reveal this strange shared history. This does not mean the particle becomes a ghost, a cloud of imagination, or a tiny indecisive traveller unable to read a map. It means that the classical idea of a particle as a small object, with a definite position at every moment, is incomplete. Quantum particles are described by rules that allow their possible positions to be distributed across space, and those possibilities can interfere with one another. That word, possible, needs care. In ordinary life, possibility often means ignorance. The keys might be in the kitchen or the bedroom because we have forgotten where we left them. The keys themselves are not doing quantum physics. They are simply waiting somewhere, probably in the least convenient place available. But in quantum mechanics, a particle's possible positions can be part of its physical description before measurement. The possibilities are not always just a list of what we do not know. They can shape what happens. This is why the claim that a quantum particle can be in two places at once is both powerful and easy to misunderstand. It does not mean an electron is a tiny marble duplicated into two separate copies. It does not mean a photon is sneaking around with a spare photon costume. It means that, before measurement, the quantum state of a particle can include more than one position or path at the same time. When those alternatives remain coherent, they can combine in ways that produce real experimental patterns. The large world teaches us that things are definite. The quantum world teaches us that definiteness is not always there in the way we expect. Between those two pictures lies one of the deepest shifts in the history of physics. The move from objects with fixed hidden properties to quantum systems described by states, probabilities, amplitudes, and measurement outcomes. So before asking how a particle can be in two places at once, it helps to see why ordinary objects cannot. They're too large, too warm, too complex, and too entangled with their surroundings. Their quantum behaviour is washed into the familiar world of definite positions, but small, carefully isolated systems can preserve the delicate structure of quantum possibility. That is where the strange promise of the title begins, not with magic, not with confusion, but with the discovery that, at the smallest scales, reality does not always choose one clear path until the rules of quantum measurement force the question. At the end of the 19th century, physics seemed to be standing on very solid ground. The great laws of motion had been laid down by Isaac Newton. The theory of electromagnetism had been brought together by James Clerk Maxwell. Heat, pressure, light, sound, electricity, magnetism, and motion all seemed to fit into a vast and elegant mechanical picture of the universe. It was tempting to imagine that nature had nearly been solved. Not completely, of course. Scientists are not usually allowed to say that without the universe immediately knocking something important off the shelf. But there was a feeling, at least among some physicists, that the main framework was already in place. The future of physics might simply involve measuring things more accurately, tidying up a few details, and perhaps finding somewhere sensible to store all the brass laboratory equipment. And yet, hidden inside those details were cracks. Not dramatic cracks at first, more like fine lines in glass, small experimental puzzles that did not seem to fit the classical picture. When scientists looked closely at heat radiation, light, and atoms, the old rules began to strain. One of the most important puzzles involved something called blackbody radiation. A blackbody is an ideal object that absorbs all radiation falling on it and then emits radiation depending on its temperature. In real life, glowing metal gives a useful hint of the idea. Heat a piece of iron, and it first glows dull red. Heat it more, and the glow becomes brighter, shifting toward orange, yellow, and eventually white. The colour and intensity of the emitted light reveal something about the object's temperature. Classical physics tried to explain this glow by treating radiation as waves of energy that could vary continuously. The problem was that the prediction went badly wrong at short wavelengths. According to the classical calculation, a hot object should emit more and more energy at ultraviolet wavelengths, rising without limit. This failure became known as the ultraviolet catastrophe, which is a wonderfully dramatic name for a graph refusing to behave itself. In reality, hot objects do not pour out infinite ultraviolet energy. The world, quite politely, does not destroy itself every time someone lights a stove. Experiments showed a very specific curve for blackbody radiation, and classical physics could not reproduce it. In 1900, Max Planck found a way to match the observed data. His solution was strange. He proposed that energy was not emitted or absorbed in a perfectly smooth continuous flow, but in discrete packets. These packets were connected to the frequency of the radiation by a tiny constant, now called the Planck constant. Planck did not begin by trying to launch a revolution. He was trying to solve a technical problem in the physics of heat and radiation. But his idea contained something radical. It suggested that at the deepest level energy exchange might come in steps, not a flowing ramp but a staircase. The steps were incredibly small, so small that in everyday life they disappear into smoothness, but they were real enough to rescue the theory from disaster. This was one of the first signs that nature might not be continuous in the way classical physics had assumed. And once the first sign appeared, another soon followed. In 1905, Albert Einstein took Planck's idea further while studying the photoelectric effect. The photoelectric effect occurs when light shines on a metal surface and causes electrons to be emitted. Classical wave theory expected the energy of the emitted electrons to depend mainly on the brightness of the light. Brighter light should mean more energy delivered to the electrons, but experiments did not behave that way. Instead, the colour or frequency of the light was crucial. Below a certain frequency, no electrons were emitted at all, no matter how bright the light became. Above that frequency, electrons could be released, and increasing the brightness increased the number of emitted electrons, rather than simply making each one more energetic. Einstein explained this by proposing that light itself could behave as individual packets of energy. These packets were later called photons. Each photon carried an amount of energy determined by the frequency of the light. Higher frequency light carried more energy per photon. Lower frequency light carried less. If a photon did not have enough energy to free an electron from the metal, then piling up more low-energy photons did not solve the problem in the simple classical way. This was deeply unsettling because light had already been shown to behave like a wave. Thomas Young's double-slit experiment had revealed interference, one of the clearest signatures of wave behaviour. Maxwell's equations had described light beautifully as an electromagnetic wave, yet Einstein's explanation showed that light also behaved like a collection of particles in certain experiments. Nature was now refusing to fit into one classical category. Light could spread and interfere like a wave, but it could also arrive and exchange energy like a particle. It was not merely one or the other, it was something deeper, something that the old words could only partially describe. Atoms brought another crack in the old picture. By the early 20th century, scientists knew that atoms emitted and absorbed light at very specific frequencies. These atomic spectra appeared as sharp lines rather than smooth rainbows. Each chemical element had its own pattern, almost like a barcode written in light. Classical physics struggled to explain this. If electrons moved around inside atoms according to ordinary electromagnetism, they should have been able to emit energy across a continuous range. Worse still, an electron orbiting a positively charged nucleus should radiate energy, lose speed, spiral inward, and collapse into the nucleus. According to that simple classical picture, atoms should not be stable, which is inconvenient given that atoms had taken the trouble to build everything. In 1913, Niels Bohr proposed a new model of the atom. He suggested that electrons could occupy only certain allowed orbits or energy levels. They could jump between these levels by absorbing or emitting specific amounts of energy. This helped explain the line spectrum of hydrogen and offered a new way to understand atomic stability. Bohr's model was not the final version of quantum mechanics. It still used partly classical images, especially the idea of electrons moving in orbit-like paths. But it marked another crucial step away from the old smooth picture. Electrons were not free to have just any energy. Atomic light was not emitted in any casual amount. Nature seemed to prefer allowed states, definite transitions, and discrete exchanges. Planck had shown that energy exchange could be quantized. Einstein had shown that light could behave as photons. Bohr had shown that atoms contained allowed energy levels. Each discovery loosened the grip of classical intuition a little more. These ideas did not yet say directly that a particle could be in two places at once. That stranger conclusion would require matter waves, wavefunctions, probability amplitudes, and superposition. But the path was now open. The old world of continuous motion and definite little objects had begun to give way to a world of quantum rules. The first cracks in classical certainty were not failures of science, they were successes. Experiments had spoken clearly, and the theory had to change to match them. Physics did not become stranger because scientists wanted it to be strange. It became stranger because careful measurements of heat, light, and atoms showed that reality was already strange, quietly and precisely beneath the surface. Light is one of the oldest mysteries in physics, partly because it feels so familiar. It fills a room, warms a face, glitters on water, and slips through a window without asking permission from the furniture. it seems gentle and ordinary, until we ask what it actually is. Then the calm little beam of sunlight begins to behave like one of nature's more elegant riddles. For a long time, scientists argued over whether light was made of particles or waves. Isaac Newton had favoured a particle-like view, imagining light as tiny corpuscles travelling through space. Later, wave theories became more powerful, especially because they explained effects that particles alone struggle to describe. Waves can spread, waves can bend, waves can overlap, and when waves overlap, they can interfere. Thomas Young's double slit experiment, first performed in the early 19th century, gave one of the clearest signs that light behaves like a wave. Young allowed light to pass through two narrow openings and fall onto a screen. If light was simply a stream of tiny pellets, one might expect two bright bands behind the two slits. Instead, the screen showed a pattern of alternating bright and dark stripes. That striped pattern is called an interference pattern. It appears when waves from the two openings meet one another. Where the waves arrive in step, crest meeting crest, they reinforce each other and form a bright region. Where they arrive out of step, crest meeting trough, they cancel each other and form a dark region. It is a beautifully simple idea, and also slightly rude to anyone hoping the universe would stay easy. This wave picture became even stronger in the 19th century through the work of James Clerk Maxwell. Maxwell showed that electricity and magnetism are deeply connected, and that changing electric and magnetic fields can travel through space as electromagnetic waves. When he calculated the speed of these waves, it matched the known speed of light. This was a remarkable moment. Light was not just brightness, it was an electromagnetic wave. In this view, visible light is only one small part of a much wider family. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays are all forms of electromagnetic radiation. They differ mainly in wavelength and frequency. Radio waves can stretch over meters or even kilometers. Visible light has wavelengths hundreds of nanometers long. Gamma rays can have wavelengths far smaller than atoms. The same underlying phenomenon appears in many different forms, from a cozy infrared heater to a medical X-ray image. By the late 19th century, the wave theory of light looked extremely successful. It explained reflection, refraction, diffraction, interference, and the connection between light and electromagnetism. If the story had ended there, light would have seemed comfortably wave-like. But nature was not finished being awkward. The photoelectric effect revealed a different side of light. When light shines on certain metals, it can knock electrons out of the surface. Classical wave theory suggested that brighter light should deliver more energy, gradually shaking electrons loose. But experiments showed something stranger. If the light's frequency was too low, no electrons were emitted no matter how bright the light became. If the frequency was high enough, electrons appeared almost immediately. In 1905, Albert Einstein explained this by treating light as packets of energy. These packets were later called photons. Each photon carries energy connected to the frequency of the light. Higher frequency light, such as ultraviolet light, carries more energy per photon than lower frequency light, such as red light. A single photon either has enough energy to free an electron from the metal, or it does not. Brightness affects how many photons arrive, but frequency determines the energy of each one. This was a profound shift. Light had behaved like a wave in interference experiments, yet it behaved like a particle when exchanging energy with electrons. It could not be described fully as only one or the other. The old categories were not completely wrong, but they were incomplete. This is the beginning of wave-particle duality. The phrase can sound as though light is sometimes a wave and sometimes a tiny marble, changing costume depending on the experiment. But that picture is too simple. A photon is not really a classical particle, and it is not really an ordinary water wave either. It is a quantum object. In some experiments, its wave-like nature is revealed through interference. In others, its particle-like nature appears through localized energy exchange. This matters because waves can pass through more than one path. A water wave reaching two gaps in a barrier does not politely choose one gap and ignore the other. It spreads through both, and the two emerging waves later combine. When light passes through two slits, the wave description naturally allows both openings to matter. The strange step comes when light is dimmed so much that photons pass through the experiment one at a time. Each photon is detected as a single localized mark on the screen, as if it arrived like a particle. Yet after many photons have arrived, the interference pattern slowly builds up. The pattern suggests that each photon's quantum state was associated with both possible paths before detection. This does not mean a photon is secretly a tiny bead taking one slit, while we are simply unsure which slit it chose. If that were the whole story, the interference pattern would not appear in the same way. The wave-like possibilities have to remain part of the description. They have to combine. Light therefore becomes the doorway into the deeper mystery. It shows that nature can be localized when measured, yet spread out in possibility before measurement. It can arrive as one small detection, while its earlier behaviour depends on more than one available route. And once light revealed this strange double nature, the question became unavoidable. Was light special, or could matter itself behave this way too? Could particles with mass, particles like electrons, also act as waves? Could something we think of as a tiny piece of matter also be associated with more than one path? The answer would carry quantum physics much closer to the title's central mystery. Light had already taught physicists that reality was not simply wave or particle. Soon, electrons would teach them that even matter is not as solidly classical as it first appears. For a long time, the wave-like behaviour of light seemed strange enough on its own. Light could spread, bend, interfere, and form delicate patterns of brightness and darkness, yet it could also arrive as individual photons delivering energy in packets. That was already a serious challenge to the tidy classical picture. But matter seemed different. Matter had mass. Matter made tables, stones, planets, hands, and laboratory equipment that somehow always ended up slightly more expensive than expected. Matter felt solid. It seemed natural to imagine that matter was made of little particles with definite positions, travelling along definite paths. Electrons, for example, had been discovered by J.J. Thomson in the late 19th century. They carried negative electric charge and had a tiny mass, far smaller than the mass of an atom. In classical terms, it was tempting to picture an electron as a very small charged bead. Perhaps not a bead anyone would want to misplace, but still a bead in spirit. Something with a location. Something that moved through space. Then Louis de Broglie made a bold suggestion. In 1924, he proposed that if light, which had long been understood as a wave, could also behave like particles, then perhaps matter, which had long been understood as particles, could also behave like waves. This was a beautifully symmetrical idea. It did not come from nowhere. Quantum theory had already shown that light had a dual nature. Planck had connected energy with frequency. Einstein had treated light as photons. Bohr had used quantum ideas to explain the allowed energies of electrons in atoms. De Broglie took these clues and asked whether wave-like behaviour might belong to all matter. The key idea was that every moving particle has an associated wavelength. This is now called the de Broglie wavelength. The wavelength depends on the particle's momentum, meaning roughly how much motion it carries. A lighter particle, such as an electron, can have a wavelength large enough to matter in atomic experiments. A heavier everyday object has a wavelength so fantastically tiny that its wave nature becomes impossible to notice in ordinary life. This is why you do not diffract noticeably through a doorway. A person walking through a door technically has a de Broglie wavelength, but it's so absurdly small that no doorway, corridor, or patient observer would ever reveal a useful interference pattern. The wave nature is not absent in principle. It is simply buried beyond practical detection. For electrons, the situation is different. Electrons are light enough that their wavelengths can be comparable to the spacing between atoms in a crystal. This means a crystal can act a little like a diffraction grating for electrons, scattering them in patterns that reveal their wave-like nature. That prediction was tested in the 1920s by Clinton Davison and Lester Germer at Bell Telephone Laboratories. They fired electrons at a nickel crystal and found that the electrons scattered in a pattern that could only be explained if the electrons had wave-like properties. The crystal's atomic structure caused the electron waves to interfere, producing preferred scattering directions. Around the same time, George Paget Thomson also demonstrated electron diffraction using thin metal films. There is a pleasing historical detail here. J.J. Thomson, George's father, had helped show that the electron was a particle, while George Paget Thomson helped show that the electron behaves as a wave. The electron, evidently not wishing to make family discussions too simple, turned out to be both in the quantum sense. Electron diffraction was a major confirmation of de Broglie's idea. Matter was not purely particle-like. It could show interference and diffraction, the classic signatures of waves. This did not mean that an electron was simply smeared out matter in the ordinary sense, like butter spread across toast. It meant that the electron's quantum state had wave-like structure. That distinction matters. When an electron is detected, it is usually found as a localized event. It leaves a spot on a detector. It transfers energy at a particular place. It does not gently arrive as a visible ripple across the whole screen, and yet before detection, its behaviour can depend on wave-like possibilities spread through space. This is where the idea of a particle being in more than one place begins to feel less like a dramatic phrase and more like a scientific necessity. If electrons can diffract, then their quantum states can interact with more than one part of a crystal. If electrons can interfere, then different possible paths must remain connected in the mathematical description. The electron is not behaving like a tiny pellet secretly following one ordinary route, while the experiment merely hides the answer from us. The evidence points to something deeper. An electron can be prepared in a state that is not localized to one sharp path. Its quantum state can extend across regions, encounter several possibilities, and later produce an outcome shaped by the combination of those possibilities. The final detection may be single and definite, but the behaviour leading to it is not classical. This was a major step toward modern quantum mechanics. Light had already blurred the boundary between wave and particle. De Broglie, Davison, Germer and Thomson showed that matter crossed the same boundary from the other direction. The things we call particles were not tiny classical objects after all. They were quantum objects, and their wave-like nature was not optional decoration. It was central to how they behaved. Once matter waves were accepted, the old image of particles as little dots moving along fixed tracks could no longer survive untouched. A new description was needed, one that could explain how a particle might be detected in one place, while still being described before measurement by a spread-out state of possibility. And that is the quiet turning point. The question is no longer whether particles can have wave-like behaviour. Experiments show that they can. The deeper question is what that wave-like behaviour means. If an electron state can spread, interfere, and respond to more than one route through an experiment, then the phrase "two places at once" begins to point towards something real, subtle, and thoroughly quantum. To understand how a quantum particle can seem to occupy more than one place at once, we need one of the most important ideas in all of quantum physics, the wave function. The wave function is not a little photograph of a particle. It is not a tiny mist floating through space in the ordinary sense. It is a mathematical description of a quantum system, and it tells us what can happen when that system is measured. In particular, it gives us the possible outcomes and the probabilities connected to those outcomes. That may sound simple at first. After all, ordinary life contains probabilities everywhere. It might rain tomorrow. A tossed coin might land heads. A misplaced phone might be under the sofa, in a coat pocket, or, for reasons known only to the household spirits, inside the fridge. But quantum probability is not quite like ordinary guesswork. In ordinary probability, uncertainty usually belongs to us. If a coin is hidden under one of two cups, we may not know which cup it is under, but we assume the coin itself is already in one definite place. The world has made its choice. We are merely catching up. Quantum mechanics is stranger. When an electron is prepared in a spread-out quantum state, the theory does not always describe it as having one hidden position that we simply have not discovered yet. Instead, the wave function can extend across different regions of space. It gives a structured description of where the electron may be found, and that structure can affect the outcome of experiments before any single position is detected. Erwin Schrödinger introduced his famous wave equation in the 1920s. His work gave physicists a way to describe how quantum systems change over time. In this picture, an electron in an atom is not treated as a tiny planet racing around a nucleus on a neat little orbit. Instead, it is described by a wave function, a quantum state spread around the nucleus in a pattern of possible measurement results. This was a huge shift. Classical physics had imagined particles as small objects with definite paths. Schrödinger's wave mechanics described particles using waves of possibility. These waves could spread, overlap, and interfere. They could form stable patterns. They could explain why atoms have certain allowed energies and why electrons do not simply collapse into the nucleus. But what did the wave function actually mean? That question was sharpened by Max Born. Born proposed that the wave function should be understood in terms of probability. More precisely, the wave function itself is connected to probability amplitudes, and from those amplitudes physicists calculate the likelihood of different measurement outcomes. If the wave function has a strong presence in one region, the particle is more likely to be found there. If it has little or no presence in another region, the particle is unlikely to be found there. A useful voiceover-friendly way to say it is this: the wave function describes the possible outcomes of a quantum system, and the probability of an outcome is found from the strength of the wave function associated with that outcome. This does not mean the wave function is merely a list of human ignorance. It is not just a note saying, the electron might be over here, or it might be over there, good luck everyone. The wave function has structure. Different parts of it can combine. They can reinforce or cancel. That is why interference patterns appear in quantum experiments. Ordinary ignorance does not create stripes of light and darkness on a screen. A wave function can. This is where the phrase, "in two places at once," begins to gain its careful scientific meaning. Imagine a quantum particle prepared so that its wave function has two separated regions where it may be detected. It is not simply that the particle is definitely in one region, and we do not know which. In many important experiments, both regions remain part of the same quantum state. Both possibilities can matter. Both can influence what happens later. When a measurement is made, however, the result is definite. The electron is found here, not everywhere. The photon strikes one spot, not the whole screen. The detector clicks in one place. Quantum mechanics gives probabilities for those clicks with astonishing accuracy, but the click itself is a single event. This creates the strange rhythm of quantum theory. Before measurement, the wave function may be spread out. It may contain several possible positions, several possible paths, or several possible outcomes. During measurement, one outcome is found. The world that seemed wide with possibility becomes narrow and specific. The Schrödinger equation describes how the wave function evolves smoothly when a quantum system is left alone. A simple way to express the idea is this. The Schrödinger equation says that the energy of a quantum system controls how its wave function changes with time. That smooth evolution is one of the reasons quantum mechanics can make such precise predictions. Yet measurement adds the puzzle. The wave function may spread across space, but observation gives one result. This is not a small detail. It sits near the center of the deepest debates in quantum physics. For now, the essential point is clear. A quantum particle is not always described as a tiny object occupying one definite position before we look. It is described by a wave function, and that wave function can include more than one possible place at the same time. Those possibilities are not vague decoration. They are part of the working machinery of the theory. So when we say a particle can be in two places at once, we're really saying that its quantum state can be spread across more than one location, with each location forming part of the same physical description before measurement. The particle is not behaving like an ordinary hidden coin. It is behaving like something deeper, quieter, and much less interested in our everyday expectations. A quantum particle being in two places at once sounds, at first, like a sentence designed specifically to upset common sense. It has the flavour of a magic trick, or a very ambitious travel plan. But in physics, the idea has a more careful name. It is called superposition. Superposition is one of the central principles of quantum mechanics. It means that a quantum system can exist in a combined state made from several possible measurement outcomes. These outcomes are not merely options in our imagination. They are part of the mathematical and physical description of the system before a measurement is made. In ordinary life, we're used to alternatives being exclusive. A lamp is on or off. A door is open or closed. A coin lands heads or tails. If we do not know which outcome has happened, we assume the answer is already fixed somewhere in the world. Our ignorance is the problem, not the lamp, the door, or the coin. Quantum superposition is different. A quantum system can be prepared in a state where more than one outcome remains genuinely present in the description. An electron can be in a superposition of possible positions. A photon can be in a superposition of possible paths. An atom can be in a superposition of energy states. A particle can have spin described as a superposition of different measurable spin outcomes. That does not mean the particle is confused. It does not mean nature has forgotten to tick a box. It means that before measurement, the quantum state has not reduced to a single classical alternative. The possible outcomes are combined. The simplest way to approach this is with position. Imagine a quantum particle prepared so that it may be found in one region of space or another. In a classical picture, we might say the particle is really in one region, and we simply do not know which. But in a true quantum superposition, that description is not enough. The two possible locations can remain part of one shared quantum state. If the two possibilities are later brought together, they can interfere with each other. This is the key sign that quantum possibilities are not ordinary guesses. If a coin is hidden under one of two cups, the two possibilities do not interfere. The possibility that the coin is under the left cup does not cancel or reinforce the possibility that it is under the right cup. They are just alternatives. But in quantum mechanics, different parts of a wave function can add together or cancel out. This is why interference patterns appear in experiments with photons, electrons, atoms, and even larger molecules under carefully controlled conditions. Superposition can also describe paths. In a double-slit experiment, a photon or electron may be sent toward two narrow openings. If no measurement is made to determine which opening it passes through, the quantum state includes both path possibilities. It is not simply that the particle sneaks through one slit while the other slit is irrelevant. Both alternatives help shape the final pattern on the detector screen. When many particles are sent through the experiment one at a time, each one is still detected as a single event. One dot appears, then another, then another. Nothing lands as a half dot or as a polite smear of uncertainty. But after many detections, the pattern reveals interference. The final arrangement of dots carries the signature of superposition. This is why the phrase "two places at once" is both useful and dangerous. It is useful because it captures the shock of quantum behaviour. Something about the particle really does involve more than one possible location or path before measurement. But it is dangerous if we imagine a normal object duplicated into two complete copies. An electron in superposition is not like a tiny football cloned onto both sides of a pitch. It is a quantum system whose state contains multiple possible outcomes. A clearer voiceover-friendly statement would be this: a quantum state can combine different possibilities, and measurement turns that combined state into one observed result. The word measurement also needs care. It does not always mean a person looking. It means a physical interaction that reveals or records information about the system. A detector, a screen, a photon, an air molecule, or a measuring device can all become part of the process. When information about the particle's position or path becomes available, the delicate superposition is usually destroyed, or at least changed so that interference can no longer be seen. This is why quantum experiments are so carefully arranged. To preserve superposition, physicists must prevent the different possibilities from becoming marked by the environment. If a photon could have travelled along two paths, but some interaction leaves a trace of which path it took, the two alternatives no longer combine in the same way. The interference disappears. Superposition is not limited to position. An electron spin can be in a superposition of possible spin measurement outcomes. A photon's polarization can be in a superposition of possible polarization directions. A qubit in quantum computing can be in a superposition of two basis states, allowing quantum information to behave very differently from classical information. In every case, the deeper idea is the same. Quantum systems are not always forced into one definite answer before measurement. So when we say a quantum particle can be in two places at once, we're using everyday language for something more precise. The particle's quantum state can include more than one possible place. Those possibilities can remain coherent. They can interfere. They can affect what is later observed. The world we see around us usually hides this behaviour, because large objects interact constantly with their surroundings. But in the quiet, carefully protected realm of quantum experiment, superposition becomes visible. It is not a failure of reality to make up its mind. It is one of reality's deeper rules. Few experiments in science are as simple to describe and as difficult to forget as the double slit experiment. At first, it seems almost too modest to carry so much meaning. There is a source of light or particles. There is a barrier with two narrow openings. There is a screen behind the barrier. Something is sent toward the openings, and something appears on the screen. That is all. No enormous machine is required in the basic idea. No black hole. No exploding star. No suspiciously glowing crystal in a secret underground laboratory. Just two slits, a screen, and nature quietly refusing to behave. The easiest way to begin is with water waves. Imagine small ripples moving across the surface of a pond toward a barrier with two gaps in it. When the wave reaches the barrier, it passes through both gaps. Each gap then becomes a new source of ripples. The two sets of ripples spread outward and overlap. Where the ripples meet in step, crest with crest, they reinforce one another. The wave becomes stronger. Where they meet out of step, crest with trough, they cancel one another. The wave becomes weaker or may disappear almost completely. This pattern of reinforcement and cancellation is called interference. Light does the same thing. In the early 19th century, Thomas Young used a version of this idea to show that light behaves like a wave. When light passes through two narrow slits, it does not simply form two bright patches on a screen, as tiny pellets might. Instead, it forms alternating bright and dark bands. The bright bands show where the light waves reinforce. The dark bands show where they cancel. So far, this is strange but manageable. If light is a wave, then the pattern makes sense. Waves can go through both openings at once. Waves can overlap with themselves. Waves can interfere. The trouble begins when the experiment is performed with individual quantum objects. Imagine sending electrons toward the double slit one at a time. Each electron reaches the detector screen as a single localized event. One dot appears, then another, then another. At first, the dots seem random, scattered in a way that gives no obvious picture. But as more electrons arrive, a pattern slowly emerges. Not two simple bands, but an interference pattern. This is the unsettling part. If each electron is sent alone, what is it interfering with? It cannot be bumping into another electron because there is no other electron travelling beside it. Each one is released separately. Yet the final pattern is the pattern of wave interference. The experiment suggests that each electron's quantum state is associated with both possible paths through the two slits. The electron is detected in one place, but before detection, its behaviour is shaped by more than one route. This is where the phrase, "the particle takes more than one path," becomes meaningful. It does not mean the electron is a tiny ball that splits neatly into two smaller balls. It does not mean half an electron sneaks through one slit while the other half takes the scenic route through the second slit. When measured, the electron is always found as a whole event. But when unmeasured, its quantum state includes both path possibilities, and those possibilities interfere. The same kind of behaviour appears with photons. A photon sent through a double slit or an interferometer can be detected as a single click, yet the probability of where that click occurs depends on interference between possible paths. The photon arrives like a particle, but its journey is described by a wave function spread across alternatives. The experiment becomes even more revealing when scientists try to find out which slit the particle goes through. If a detector is placed near the slits and records the path, the interference pattern disappears. The screen no longer shows the same alternating bands. Instead, the pattern becomes more like what one would expect from particles passing through one opening or the other. This is not because the detector politely frightens the electron into behaving. It is because measuring the path changes the quantum situation. Once which path information exists, the two alternatives are no longer combined in the same coherent way. They cannot interfere as before. The quantum state has become linked with the measuring device, and the delicate relationship between the two paths has been disturbed. That detail is crucial. The mystery is not simply that we do not know which slit the particle used. The mystery is that, if the path is not measured, the final result behaves as though both paths were part of the particle's quantum description. If the path is measured, the interference vanishes. Knowledge in this case is not just a note written in the scientist's notebook. It is a physical interaction that changes what can happen. The double slit experiment therefore gives one of the clearest examples of spatial superposition. A quantum particle can be prepared so that its possible path goes through one slit and through the other slit as part of one combined state. The alternatives remain open, not as ordinary ignorance, but as interfering possibilities. And yet the screen always receives definite marks. Each electron or photon is found in one place. This is the quiet rhythm of quantum physics again. Before measurement, spread out possibility. At measurement, one actual result. Over many repeated trials, a precise pattern emerges, revealing the hidden structure of the wave function. This is why the double slit experiment sits so close to the heart of quantum mechanics. It shows the difference between classical uncertainty and quantum superposition. A classical particle would go through one slit, whether or not anyone knew which. A classical wave would pass through both and spread across the screen. A quantum particle does something stranger. It is detected as a single event, but its probabilities are shaped by a wave-like state that includes both paths. So when people say that a particle can be in two places at once, the double slit experiment is one of the strongest reasons they say it. The particle is not seen as two little objects. It is not photographed halfway through both slits like a tiny celebrity caught leaving two restaurants. But the interference pattern tells us that both possible paths were physically relevant. The double slit does not make quantum physics easy. It makes the mystery precise. It shows that the small world is not built from ordinary objects with merely hidden positions. It is built from quantum states, possibilities, interference, and measurement. And in that deeper language, a particle can travel through an experiment as though two routes belong to one reality, until the final moment when nature gives just one answer. Measurement is one of the strangest words in quantum physics, because it sounds so ordinary. In everyday life, measuring something feels passive. You measure a table, and the table does not seem offended. You weigh a bag of flour, and the flour does not suddenly reconsider its identity. Measurement appears to reveal facts that were already there. In quantum mechanics, measurement is more delicate. It is not simply a human looking at a particle and discovering what the particle was already doing in a neat, classical way. Measurement is a physical interaction. A quantum system becomes linked with something else: a detector, a screen, an atom, a photon, a measuring device, or even part of the surrounding environment. That interaction can change what kinds of quantum behaviour remain possible. This matters because quantum systems can exist in superpositions before measurement. A photon can be in a superposition of paths. An electron can be in a superposition of possible positions. An atom can be in a superposition of energy states. As long as the alternatives remain coherent, they can interfere with one another. But when a measurement records which alternative happened, that delicate combination is usually lost. The double slit experiment shows this very clearly. If an electron passes through a double slit without any detector checking which slit it used, an interference pattern can build up on the screen. The electron is detected as one dot, but the pattern formed by many electrons reveals that both paths were part of the quantum description. The possibilities remained combined. Now place a detector near the slits. If the detector records which slit the electron passes through, the interference pattern disappears. The electron still arrives at the screen. The detector still clicks. The experiment still works in the basic mechanical sense. But the wave-like combination of both paths is gone. The result becomes more like a particle going through one slit or the other. This does not happen because a scientist has gained forbidden knowledge, and the universe is being dramatic about privacy. It happens because the measurement is a real physical process. To learn which path the electron took, the detector must interact with it. That interaction links the electron's state with the detector's state. Once the path information exists in the physical world, the two alternatives can no longer interfere in the same way. This is why the phrase "observation changes reality" can be misleading. It can sound as though consciousness itself has some mysterious power to force the universe into making decisions. In ordinary quantum mechanics, that is not necessary. A detector can measure without a mind. A photographic plate can record a mark without understanding it. A stray air molecule can bump into a particle without writing a thoughtful essay about the encounter. The important thing is not human awareness. The important thing is whether information about the quantum system becomes physically available. If the environment carries away information about which path a particle took, then interference can be destroyed even if no person ever reads the result. This leads to the measurement problem, one of the deepest puzzles in quantum theory. When a quantum system is not being measured, its wave function evolves smoothly according to the Schrödinger equation. The wave function can spread, split into alternatives, and change continuously over time. But when a measurement is made, we do not experience a spread of outcomes. We see one result. The electron is found here, the photon strikes there, the detector gives one answer. The mathematical rules of quantum mechanics are extremely successful at predicting the probabilities of those answers. They tell us how likely each outcome is. But the question of exactly how one definite result emerges from a spread of possibilities is where interpretation begins. Niels Bohr and Werner Heisenberg were closely associated with what became known as the Copenhagen interpretation. This way of thinking emphasized that quantum theory predicts the outcomes of measurements, and that classical concepts such as position and momentum must be used carefully when discussing what can actually be observed. It did not present the quantum world as simply a smaller version of the everyday world. It insisted that measurement plays a central role in what can be meaningfully said. One common way of describing measurement is wave function collapse. Before measurement, the wave function may contain several possible outcomes. After measurement, only one outcome is found. Collapse is the name often given to that transition from many possibilities to one observed result. It is useful language, but it also hides a great deal of mystery. Different interpretations of quantum mechanics understand collapse in different ways. Some treat it as a real physical process. Some treat it as an update of information. Some avoid collapse altogether by describing all outcomes as part of a larger quantum reality. Whatever interpretation one prefers, the practical experimental fact remains clear. Superposition survives only when the alternatives remain coherently connected. If the particle's path, position, or state becomes recorded by a detector or leaked into the environment, the interference that revealed superposition disappears. This is why quantum experiments are often so carefully isolated. Physicists use vacuum chambers to reduce collisions with air molecules. They use low temperatures to reduce thermal disturbance. They shield systems from stray radiation and vibration. They do not do this because quantum particles are shy, though sometimes it does feel that way. They do it because superposition is fragile. A particle can behave as though it is in two places at once, only while those two alternatives remain part of one coherent quantum state. The moment the world gains reliable information about which place it is in, the situation changes. The particle is then found in one place, and the strange interference between possibilities is lost. Measurement, then, is not just looking. It is the point where quantum possibility becomes tied to physical record. It is where the open, spread-out description of a system gives way to a definite outcome. And that is why the quantum world can seem to hold several paths at once, while the measured world presents us with only one. In everyday life, probability usually means that we do not know something yet. The answer is already out there somewhere, sitting quietly behind the curtain, and probability is just our way of admitting that we have not looked. If a coin is hidden under one of two cups, we might say there is a chance it is under the left cup, and a chance it is under the right cup. But nobody imagines the two possibilities are physically blending together. The coin is not under the left cup in a way that cancels out the coin under the right cup. It is not creating a mysterious cup-based interference pattern across the kitchen table. It is simply in one place, while we are uncertain. The same is true for many ordinary situations. A shuffled card is somewhere in the deck. A lost key is somewhere in the house. A train may arrive at a certain time, although this example sometimes enters the realm of advanced philosophy. In all these cases, probability describes limited knowledge about a definite situation. Quantum probability is different. In quantum mechanics, probabilities come from something called probability amplitudes. These are not ordinary probabilities. They are the pieces of the wave function that describe possible outcomes. When physicists calculate what may happen in a quantum experiment, they do not simply add ordinary chances together. They combine probability amplitudes, and these amplitudes can reinforce one another or cancel one another out. This is the heart of quantum interference. A simple way to picture interference is with water waves. If two ripples meet crest to crest, they build a larger ripple. This is constructive interference. If one ripple's crest meets another ripple's trough, they can reduce or cancel each other. This is destructive interference. The water is not choosing randomly between two ordinary options. The waves are physically combining. In quantum physics, the wave function behaves in a mathematically similar way. Different parts of the wave function can combine. Some possible paths increase the chance of a particle being detected in a certain place. Other possible paths reduce that chance. This is why an interference pattern can have bright and dark bands, or regions where particles arrive often, and regions where they rarely appear. The double slit experiment makes this especially clear. If electrons are fired one at a time through two open slits, each electron is detected as one spot on the screen. But after many electrons have arrived, a pattern appears. Some regions receive many detections, other regions receive very few. This is not what we expect from tiny classical pellets passing through one slit or the other. It is the pattern of interference. The important point is that the interference is not between two electrons travelling together. The electrons can be sent one at a time. Each electron's quantum state includes the possible route through one slit and the possible route through the other slit. These alternatives are represented by probability amplitudes. When the amplitudes reach the screen, they combine. In some places they reinforce, in others they cancel. That is why quantum possibilities are not ordinary guesses. If the electron was simply going through one definite slit while we happened not to know which one, there would be no reason for the two possibilities to cancel each other. Ignorance does not make empty stripes on a detector. A hidden coin does not interfere with its own alternative hiding place, but a quantum wave function can. Richard Feynman gave one of the most powerful ways to think about this with his path integral formulation of quantum mechanics. In this approach, a quantum particle is described as receiving contributions from many possible paths between its starting point and its final detection. Each path contributes a probability amplitude. When all these amplitudes are combined, most possibilities cancel out, while some reinforce and help shape the result we actually observe. This does not mean a particle literally wanders along every imaginable path in the ordinary sense, like a very small tourist determined to inspect every possible route before choosing a destination. It means that quantum theory can calculate outcomes by treating many possible paths as contributing to the final amplitude. The mathematics is precise, and the conceptual message is striking. The final result is shaped by alternatives that classical physics would have dismissed. This is why superposition has real experimental force. A quantum particle in a superposition is not merely one definite thing hidden behind a curtain. The different components of the state can produce observable effects. They can interfere. They can change the final pattern of detections. They can make some outcomes more likely and others less likely. Ordinary probability only tells us how surprised we should be when an unknown fact is revealed. Quantum probability helps determine what facts can appear in the first place. This is also why measurement matters so deeply. When which path information is recorded, the interference disappears. The alternatives no longer combine as parts of one coherent quantum state. The probability amplitudes no longer reinforce and cancel in the same pattern. The experiment begins to look more classical, as though the particle took one route or the other. So when we say a particle can be in two places at once, the strongest evidence is not that someone caught it sitting visibly in two locations. The evidence is subtler and more powerful. The alternatives behave as though they both mattered. They combine like waves, they interfere, they leave behind patterns that cannot be explained by ordinary ignorance about a single hidden path. Quantum mechanics replaces the simple idea of maybe here, maybe there with something deeper. A particle state can contain here and there as parts of one physical description. Those parts can meet again, reinforce, cancel, and shape what is finally observed. That is the strange beauty of probability amplitudes. They turn possibility into something structured. They make uncertainty active. They show that before measurement, the quantum world is not merely unknown, it is genuinely arranged according to rules that allow different possible histories to overlap. And from that overlap comes one of the quietest but most profound facts in physics. A particle does not always behave as though it had one ordinary path all along. Sometimes, the possibilities themselves are part of reality's machinery. One of the quiet lessons of quantum physics is that the universe does not always allow us to pin things down as neatly as we would like. Classical physics gives us a reassuring picture. An object has a position. It has a motion. If we are clever enough, careful enough, and perhaps surrounded by enough polished brass instruments, we can measure both as precisely as we please. For large objects, this works beautifully. A tennis ball has a position and a velocity. A planet has an orbit. A spacecraft has a trajectory that can be calculated with remarkable accuracy. There are uncertainties, of course, but they usually come from imperfect instruments, tiny disturbances, or incomplete information. The object itself is assumed to possess definite properties all along. Quantum mechanics changes that assumption. Werner Heisenberg introduced one of the central principles of quantum theory in the 1920s. It is now called the uncertainty principle. At its heart is the idea that certain pairs of properties cannot both be defined with unlimited precision at the same time. The most famous pair is position and momentum. Position means where something is. Momentum means how much motion it carries, taking into account both its mass and its velocity. In everyday language, momentum tells us something about where an object is heading and how strongly it is moving. A rolling bowling ball has more momentum than a drifting feather, which is one reason you would rather catch the feather, usually. In classical physics, position and momentum can both be perfectly definite. A particle can be here, moving this way, at this speed. Any uncertainty belongs to the observer. But in quantum mechanics, position and momentum are linked in a deeper way. The more tightly a particle's position is defined, the less precisely its momentum can be defined. The more precisely its momentum is defined, the less sharply its position can be defined. A voiceover-friendly way to state the principle is this. The uncertainty principle says that the uncertainty in position multiplied by the uncertainty in momentum cannot be smaller than a fixed quantum limit. That fixed limit is connected to the Planck constant, the tiny number introduced by Max Planck when he studied blackbody radiation. The Planck constant is extremely small, which is why uncertainty does not noticeably affect ordinary objects. For a football, a chair, or a sleeping cat that has wisely avoided Schrödinger's box, the quantum limit is so tiny compared with the object's size and mass that classical certainty works perfectly well. For electrons, photons, atoms, and other small quantum systems, the limit matters. One way to understand this is through waves. A wave with a very well-defined wavelength stretches out over space. Because its wavelength is clear, its momentum is also more clearly defined. But because the wave is spread out, its position is not sharply localized. It is not concentrated at one exact point. To make a wave more localized, different wavelengths must be combined. A shortwave packet can be built by adding many wave components together. This gives a better defined position, but it also introduces a wider spread of momenta. The particle becomes easier to place, but harder to assign one exact momentum. This is not just a problem of measurement. It is not simply that our instrument's too clumsy, or that looking at an electron bumps it in an unfortunate way. Measurement disturbance can happen, but the uncertainty principle is deeper than that. It arises from the structure of quantum states themselves. This matters directly for the idea of a particle being in two places at once. In the classical picture, a particle should always have a precise position, whether or not we know it. Quantum mechanics says that a particle's position may not be defined in that way before measurement. Its wave function can be spread across space. It can give probabilities for where the particle may be found, without the particle already possessing one ordinary classical location. The uncertainty principle helps us see why this is not just a strange optional feature. If a particle is described by a spread-out wave function, then its position is naturally uncertain. It is not always sitting at one invisible point beneath the mathematics. The spread is part of the physical description. This also helps explain atoms. In the classical picture, electrons orbiting a nucleus should radiate energy, spiral inward, and collapse. But electrons in atoms are not little planets travelling along neat paths. They occupy quantum states called orbitals. Their positions are described by probability distributions around the nucleus. The uncertainty principle plays a role in their stability. If an electron was squeezed too tightly into the nucleus, its position would become extremely well defined. That would make its momentum highly uncertain, giving it a large range of possible motion. In simple terms, confining an electron too much makes it energetically restless. Quantum mechanics does not allow the electron to sit calmly inside the nucleus, like a tiny marble placed in a bowl. So the uncertainty principle is not merely a limit on knowledge. It is part of the reason matter has structure. It helps explain why atoms have size, why electrons form orbitals, and why the familiar world does not collapse into featureless density. It also softens the idea that reality must always be sharply drawn before anyone looks. In the quantum world, some properties are not waiting with perfect values hidden behind a curtain. The state itself may be broad, distributed, and filled with structured possibility. A quantum particle can be found in one place when measured, but before that measurement, its position may be described by a wave function spread across many possible places. Heisenberg's uncertainty principle tells us that this is not a failure of patience, eyesight, or laboratory tidiness. It is one of the basic rules of the small world. Reality, at the quantum scale, is not always a pinpoint. Sometimes it is a range of possibility, held together by precise laws, until measurement gives one clear answer. The old picture of the atom is wonderfully tempting. A tiny nucleus sits at the centre, and electrons whirl around it like planets orbiting a star. It is neat. It is memorable. It looks good in school diagrams. It also has the slight disadvantage of not being how atoms really work. The planetary image became popular because it gave people something familiar to hold on to. The nucleus, discovered through the work of Ernest Rutherford, is small, dense, and positively charged. Electrons are negatively charged and are found around it. In a simple drawing, it feels natural to place the electrons on little circular tracks, racing around like miniature moons. But if electrons really behaved like tiny planets, atoms would be in serious trouble. According to classical electromagnetism, an accelerating charged particle should emit radiation. An electron travelling in a circular orbit would constantly be accelerating, because its direction is always changing. That means it should lose energy. As it lost energy, it should spiral inward toward the positively charged nucleus. In an extremely short time, the atom would collapse. Since atoms have not collapsed, and since the furniture around us continues to take its role as furniture very seriously, something in the classical picture must be wrong. Niels Bohr offered one of the first major quantum answers in 1913. In Bohr's model of the hydrogen atom, the electron could occupy only certain allowed orbits with specific energies. It could not simply spiral through every possible path. It could jump between allowed energy levels by absorbing or emitting light of specific frequencies. This helped explain the line spectrum of hydrogen. Hydrogen does not emit every possible colour of light in a smooth blend. It emits specific lines, corresponding to specific energy differences. Bohr's model gave a powerful early explanation for this, and it showed that atoms were governed by quantum rules rather than ordinary classical motion. But Bohr's model was still only a stepping stone. It kept the image of orbiting electrons, even though the deeper theory would eventually move beyond it. With Erwin Schrödinger's wave mechanics, electrons in atoms were no longer treated as tiny planets on fixed tracks. They were described by wave functions. These wave functions form atomic orbitals. An orbital is not an orbit. The difference matters. An orbit is a path, like the track of a planet around the sun. An orbital is a quantum state that gives the probability distribution for where an electron may be found if measured. In other words, an electron in an atom is not usually sitting at one exact point on a little circular road. Its quantum state is spread around the nucleus in a particular pattern. Some regions have a higher probability of detection. Other regions have a lower probability. The electron may be found in one place when measured, but before measurement, its state is described across the orbital. This is one of the clearest everyday examples of quantum weirdness hiding inside ordinary matter. Every atom in your body depends on electrons that are not behaving like little beads moving around little tracks. They are described by spread-out quantum states. The shapes of orbitals can be surprisingly rich. Some are roughly spherical, others have dumbbell-like shapes. Others are more complex with several lobes and regions where the probability of finding the electron is extremely low. These shapes are not decorative. They help determine how atoms bond, how molecules form, and why chemistry has the structure it does. The scale is also important. An atom is mostly empty space by ordinary standards. A typical atom is roughly a 10 billionth of a metre across. The nucleus is about 100,000 times smaller than the atom as a whole. If the atom were expanded to the size of a large stadium, the nucleus might be more like a tiny object near the centre, while the electron's quantum state would occupy the vast surrounding region. That does not mean the electron is smeared through the atom like fog in a room. the wave function is not ordinary mist. It is a quantum description of possible measurement outcomes. But it does mean that the electron is not properly described as a classical dot with a definite track. Wolfgang Pauli added another essential piece with the Pauli exclusion principle. This principle says that no two electrons in an atom can occupy exactly the same quantum state. Because of this, electrons fill different orbitals and energy levels. This structure helps create the periodic table of elements. Without the Pauli exclusion principle, matter would be radically different. Electrons would not arrange themselves into the familiar shells that give elements their chemical personalities. Carbon, oxygen, iron, gold, and the rest would not behave as they do. Chemistry would lose its architecture, which would be inconvenient for life, planets, tea, and quite a lot of biscuits. Electron orbitals also help explain chemical bonding. When atoms come together, their electron wave functions can overlap and combine. The resulting molecular orbitals describe how electrons are shared or distributed across a molecule. In covalent bonds, for example, electrons are not simply tucked neatly beside one atom or another. They can occupy quantum states spread across both atoms. This connects directly to the idea of being in more than one place at once. Inside atoms and molecules, electrons are often described by quantum states extending across regions of space. In a molecule, an electron may be associated with more than one atomic center. In certain chemical systems, electrons can be delocalized across several atoms, helping produce the properties of metals, aromatic molecules, and many materials. So the title's mystery is not only found in dramatic laboratory experiments with slits and screens. It is woven into the ordinary stability of matter. The electrons in atoms do not behave like tiny planets, because classical planets would make unstable atoms. They behave as quantum systems with allowed states, probability distributions, and wave functions. When an electron is measured, it is found in one place. But when it is bound inside an atom, its state can be spread around the nucleus. It can belong to an orbital rather than a path. It can help form matter precisely because it is not forced into the narrow role of a classical particle. The atom, then, is not a miniature solar system. It is a quantum structure. Its stability comes from wave functions, uncertainty, allowed energies, and the Pauli exclusion principle. The solid world around us is built from particles that are not solid in the old classical sense. That is one of the most beautiful turns in physics. The reason matter feels stable is not because electrons behave like tiny pieces of ordinary matter. It is because they do not. So far, the idea of being in two places at once has mostly meant position. A particle's quantum state can be spread across space. An electron can be associated with more than one path in a double-slit experiment. A photon can travel through an interferometer as though more than one route matters before the final detection. But superposition is not limited to location. Quantum mechanics is stranger and more general than that. A particle can also be in a superposition of other measurable properties such as spin, polarization, energy, or momentum. The title points us toward one of the most vivid examples, but the deeper rule is broader. Quantum systems can exist in combined states of several possible outcomes. One of the most important examples is spin. The word spin sounds familiar, which is slightly dangerous. In ordinary life, spin means rotation. A planet spins, a wheel spins, a tennis ball spins after a dramatic serve. So it is natural to imagine an electron spinning like a tiny charged marble. But quantum spin is not quite that. An electron is not a little planet turning on an axis. Spin is an intrinsic quantum property, built into the particle itself. This property behaves in ways that resemble angular momentum, and it affects how particles respond to magnetic fields. But it is not classical rotation. If we picture the electron as a tiny sphere spinning fast enough to create its quantum spin, the picture breaks down. The electron is too small, and the required surface motion would not make physical sense. So spin must be treated as a genuinely quantum property. One of the most famous demonstrations of this came from Otto Stern and Walter Gerlach in 1922. Their experiment sent silver atoms through a non-uniform magnetic field. If the atoms behaved classically, one might expect their magnetic orientations to vary smoothly, producing a continuous smear on a detector. Instead, the beam split into distinct parts. This showed that the measured spin-like property was quantized. The atoms did not land in every possible place corresponding to every possible orientation. They appeared in discrete outcomes. The result was one of the key pieces of evidence that quantum properties do not always vary smoothly like classical quantities. For an electron, spin measurements along a chosen direction give particular possible outcomes. Before measurement, however, the electron can be prepared in a superposition of those outcomes. It is not simply that the electron secretly has one classical spin direction, and we have not discovered it yet. In quantum mechanics, the spin state can be genuinely combined. This is similar in spirit to a particle having two possible paths. Instead of saying the particle is in a superposition of being here and there, we might say it is in a superposition of spin outcomes relative to a certain measurement direction. The details are different, but the principle is the same. The quantum state contains more than one possible result before measurement. Photon polarization gives another beautiful example. Light is an electromagnetic wave, and polarization describes the orientation of its electric field. In classical terms, polarized light can be vertical, horizontal, or oriented at other angles. Sunglasses with polarizing filters use this property to reduce glare, especially from flat surfaces such as water or roads. Very helpful for driving, fishing, and looking mysteriously thoughtful beside a lake. For individual photons, polarization becomes quantum. A photon can be prepared in a superposition of different polarization states. When measured with a polarizing filter or detector, one definite result is obtained. But before measurement, the photon state can combine different polarization possibilities. This is not just an abstract curiosity. Photon polarization is widely used in quantum optics, quantum communication, and experiments on the foundations of quantum mechanics. It provides a clean way to study superposition, measurement, and entanglement, because photons can be produced, manipulated, and detected with great precision. Spin and polarization help make the central idea clearer. Two places at once is only one version of a larger quantum theme. A quantum system can be in more than one possible state at once, depending on what property is being considered. It might be more than one path. It might be more than one spin outcome. It might be more than one polarization direction. It might even be more than one energy state. Atoms can occupy superpositions of energy levels, and these superpositions matter in atomic clocks, spectroscopy, lasers, and quantum information experiments. A carefully prepared atom is not always simply in one energy state in the classical sense. It can be described by a combined state, and the way that combined state evolves can be measured with extraordinary precision. This is also the foundation of the qubit in quantum computing. A classical bit is treated as one of two values. A qubit can be in a superposition of two basis states. This does not mean a quantum computer magically tries every answer at once in a simple way, but it does mean quantum information can be manipulated through superposition, interference, entanglement, and measurement. The same principle that makes the double slit experiment strange also makes quantum computing possible. The important lesson is that superposition belongs to the structure of quantum theory itself. It is not a special trick reserved for particles moving through slits. It appears wherever quantum states can be combined coherently. Position, spin, polarization, energy, and other properties can all show it. And every time the pattern is similar. Before measurement, the quantum state can contain several possible outcomes. During measurement, one result is found. If the alternatives remain coherent, they can interfere or produce effects that reveal the combined nature of the state. If the environment records the outcome too early, the delicate quantum behaviour fades. So when we ask why a particle can be in two places at once, We are really asking why quantum systems are not always locked into one classical property before observation. The answer is not limited to space. At the smallest scales, nature allows combined states. It allows possibility to have structure. It allows a particle's reality to be described not by one fixed answer, but by a quantum state containing several answers that only become definite when measured. That may sound unsettling at first, but it is also what makes atoms stable, light useful, chemistry possible, and modern quantum technology real. Superposition is not an exception to the rules of nature. It is one of the rules. If quantum particles can exist in superpositions, then a very natural question appears. Why does the world around us look so ordinary? Why do electrons and photons get to behave as though more than one path is open, while a chair remains stubbornly in one corner of the room? Why can an atom be placed into a delicate combined state, while a mug of tea refuses to be both on the desk and across the room, however useful that might be on a tired morning? The answer is not that large objects are outside quantum physics. Everything is made from quantum ingredients. Chairs, planets, people, clouds, cats, teaspoons, and slightly mysterious cables in drawers are all built from atoms. At the deepest level, they are quantum systems too. The difference is that large objects do not stay isolated. A quantum superposition depends on coherence. Coherence means that the different parts of a quantum state maintain a definite relationship with one another. In a double-slit experiment, the path through one slit and the path through the other slit can remain coherent. Because of that, the two possibilities can interfere. They can reinforce or cancel, creating the pattern that reveals the particle's wave-like behaviour. But coherence is fragile. If the particle interacts with the environment in a way that records information about its path, position, or state, the alternatives stop interfering. The quantum possibilities are still part of the deeper description, but the interference becomes practically unavailable. This process is called decoherence. Decoherence is one of the most important ideas for understanding why quantum weirdness seems to disappear in everyday life. It explains how quantum systems become entangled with their surroundings so quickly and thoroughly that their delicate superpositions no longer behave like visible superpositions. The basic idea is simple enough. Imagine an electron in a superposition of two possible paths. As long as nothing in the universe can tell which path it took, the two paths may remain coherent. But if a photon scatters from the electron, or a gas molecule bumps into it, or a detector records some trace of its location, information about the path leaks into the environment. The electron is no longer described on its own. It has become linked with the outside world. That link matters. The environment now carries a record even if no person reads it. The record might be unimaginably tiny. It might be spread across scattered photons, vibrations, or air molecules. But once the information exists physically, the original alternatives cannot interfere in the same clean way. This is why measurement does not require consciousness. A particle does not wait for a scientist to glance over and say, "Aha." The surrounding world is more than capable of ruining a quantum superposition on its own. Nature, it turns out, has no shortage of nosy air molecules. For small systems, decoherence can sometimes be delayed. Physicists use vacuum chambers to reduce collisions with air. They use low temperatures to limit thermal motion. They shield experiments from stray radiation and vibration. They prepare photons, ions, atoms, or superconducting circuits with extraordinary care. Under these conditions, superpositions can survive long enough to be studied and used. For large warm objects, the situation is very different. A chair in a room is constantly interacting with its environment. Air molecules strike it. Infrared radiation is emitted and absorbed. Light bounces from its surface. Its atoms vibrate. The floor presses against it. Every tiny interaction carries away some information about where the chair is. These interactions happen unbelievably quickly. For macroscopic objects, decoherence can occur on timescales so short that they are effectively impossible to notice directly. The object's possible quantum alternatives lose the ability to interfere almost instantly. The result is the familiar classical world, where things appear to have definite positions. Heinz-Dieter Zeh was one of the early physicists to emphasize the importance of environmental interaction in quantum measurement. Wojciech Zurek later developed major ideas in decoherence theory and quantum Darwinism, exploring how the environment selects certain stable states and spreads information about them. These ideas helped explain why the world we experience looks classical, even though its foundations are quantum. It is important to be careful here. Decoherence explains why interference disappears and why large objects seem to have definite classical properties. It does not solve every philosophical question about measurement. It does not, by itself, tell everyone exactly why one specific outcome is experienced rather than another. Different interpretations of quantum mechanics still answer that deeper question in different ways. But decoherence explains an enormous part of the puzzle. It shows why superposition is easy to see in carefully isolated systems and almost impossible to see in everyday objects. It explains why an electron can pass through an experiment with two possible paths, while a football does not visibly take two routes into the goal. Though to be fair, some goalkeepers may strongly suspect it. The title's mystery, therefore, has a boundary. Quantum particles can behave as though they are in two places at once, when their alternatives remain coherent. They can interfere because the different possibilities are still part of one quantum state. But when information leaks into the environment, coherence is lost. The superposition becomes hidden from observation, and the system behaves more classically. This is why the quantum world is not absent from ordinary life. It is buried beneath constant interaction. The atoms in a chair still obey quantum mechanics. The electrons still occupy quantum states. The bonds holding the material together still depend on wave functions and the Pauli exclusion principle. But the chair as a whole is far too entangled with its environment to show a clean, visible superposition of being here and there. Decoherence is the bridge between the strange and the familiar. It does not make quantum mechanics less real. It explains why its strangest features are so carefully concealed. The universe does not stop being quantum when objects become large. It simply becomes noisy, busy, and deeply interconnected. And in that busy exchange of information, the delicate music of superposition fades into the steady rhythm of the classical world. No image in quantum physics is more famous or more unfairly blamed for confusion than Schrödinger's cat. The phrase often appears whenever people want to make quantum mechanics sound dramatic. A cat is alive and dead at the same time. A box is mysterious. A scientist waits outside. Somewhere in the background, common sense quietly asks to be excused. But the original point of the thought experiment was more subtle than the popular version suggests. Erwin Schrödinger introduced the cat thought experiment in 1935. He was responding to the strange implications of quantum mechanics, especially the idea that a quantum system can exist in a superposition before measurement. Schrödinger was not proposing a practical experiment involving an actual cat. He was not writing a guide for irresponsible pet ownership. He was pointing to a deep problem in the theory. The setup is usually described like this. Imagine a cat inside a sealed box. Also inside the box is a device connected to a quantum event, such as the possible decay of a radioactive atom. If the atom decays, the device releases poison, and the cat dies. If the atom does not decay, the cat lives. According to quantum mechanics, before measurement, the radioactive atom may be described as being in a superposition of decayed and not decayed. If the atom is in a superposition, and the atom is linked to the device, and the device is linked to the cat, then what should we say about the whole system? Is the cat also in a superposition of alive and dead until someone opens the box? That is the uncomfortable question Schrödinger wanted to expose. The point was not that cats really wander around in everyday life being alive and dead in some visible mixed condition. The point was that if quantum superposition applies to microscopic systems, and microscopic systems can affect macroscopic objects, then we need to explain how the definite world we experience emerges from quantum rules. Somewhere between a radioactive atom and a cat, the mystery becomes impossible to ignore. This matters because quantum mechanics works beautifully for small systems. An atom can be in a superposition of energy states. An electron can be in a superposition of paths. A photon can be in a superposition of polarizations. These ideas are not optional decorations. They're tested experimentally and used in real technologies. But a cat is not an electron. A cat is warm, complex, breathing, metabolizing, and constantly interacting with its environment. It contains an enormous number of atoms. It emits heat. It scatters light. Its molecules are moving and vibrating. Its body is filled with chemical processes, electrical signals, air movement, and countless interactions with the box around it. This is why the cat is not a good literal example of a clean, maintained macroscopic superposition. Decoherence would occur extremely quickly. The possible alternatives would become entangled with the environment almost immediately. Information about the cat's condition would spread into air molecules, thermal radiation, and the internal state of the entire box. The delicate coherence required for visible interference between alive and dead alternatives would vanish far too quickly to treat the cat like a neatly isolated electron. So Schrödinger's cat is not best understood as a claim that large animals really sit around in ghostly half-states until humans check on them. It is a challenge. It asks how far we can apply the mathematical rules of quantum mechanics. It asks what measurement means. It asks why microscopic superpositions are real and experimentally visible, while macroscopic superpositions seem to disappear into ordinary definite outcomes. The thought experiment also shows why the phrase, "in two places at once," becomes much more difficult as objects become larger. For an electron in a double-slit experiment, spatial superposition can be tested by looking for interference. The electron's possible paths remain coherent, and the final pattern reveals that both paths mattered. For a large object, maintaining coherence between two distinct states becomes enormously harder. A warm, everyday object is constantly leaking information into its surroundings. If an object were in a superposition of being in one place and another place, light and air molecules would almost instantly carry away information about its position. Once that information exists in the environment, the alternatives can no longer interfere in the way required to reveal a clean quantum superposition. This is the trouble with scaling up. Quantum rules do not suddenly stop applying when something becomes large. There is no clear sign in nature saying, "Quantum mechanics ends here. Please use classical physics from this point onward." Instead, the transition is gradual and practical. The more complex, warm, massive, and environmentally connected a system becomes, the harder it is to preserve coherent superposition. Modern experiments have pushed this boundary further and further. Physicists have demonstrated interference with atoms and large molecules. They have created superpositions in superconducting circuits and trapped ions. They have built delicate systems where collective properties behave quantum mechanically. These are not cats, but they show that the border between quantum and classical is not simply about size. It is about isolation, coherence, control, and interaction with the environment. Schrödinger's cat remains powerful because it turns an abstract mathematical puzzle into an image we cannot easily ignore. A radioactive atom in superposition may feel remote. A cat in a box feels immediate. The thought experiment forces us to ask why one kind of superposition seems acceptable, while another feels absurd. And that feeling of absurdity is useful. It tells us exactly where our classical intuition is struggling. We are comfortable with particles being strange because they are far away from everyday experience. We are less comfortable when the same logic appears to reach into the world of familiar objects. The careful answer is that the quantum world does not vanish at large scales, but its most delicate features become hidden by decoherence. A particle can behave as though it is in two places at once when its alternatives remain coherent. A cat, a chair, or a person cannot show that behaviour in ordinary conditions because the environment records their state far too quickly. So Schrödinger's cat is not just a strange story about life, death, and a very unfortunate box. It is a doorway into the deepest question of quantum measurement. How does a world made from quantum possibilities become the definite world we actually see? The answer is still discussed, debated, and refined. But the lesson is already profound. Quantum superposition is real. Scaling it up is difficult, and the calm, definite world around us may be less fundamental than it appears. For a long time, superposition sounded like something that belonged only to the smallest and most delicate parts of nature. Photons, electrons, and individual atoms could behave in strange quantum ways, while anything larger seemed safely classical. But one of the remarkable achievements of modern physics is that scientists have learned how to push quantum superposition into larger and larger systems. This does not mean researchers are placing bicycles, teapots, or sleeping cats in two places at once. The universe remains disappointingly unhelpful for anyone hoping to keep a spare cup of tea on the other side of the room. But it does mean that the boundary between the quantum and classical worlds has been tested with increasing care. A good starting point is interferometry. An interferometer is a device that splits a wave-like system into different paths and then brings those paths back together. If the paths remain coherent, they can interfere. This makes interferometers ideal for studying whether a particle, atom, or molecule has behaved as though more than one path was part of its quantum state. Neutron interferometry provided one early and important example. Neutrons are particles found in atomic nuclei, and they are far more massive than electrons. Yet carefully controlled neutron beams can show interference. Facilities such as the Institut Laue-Langevin in France helped make neutron research a major part of modern experimental physics. These experiments showed that matter waves were not limited to the lightest particles. Larger particles could also be split, guided, and recombined in ways that revealed quantum superposition. Atom interferometry pushed the idea further. Atoms are composite objects made from electrons surrounding a nucleus of protons and neutrons. They have internal structure. They are not elementary particles, yet atoms can still behave as coherent quantum waves under the right conditions. In atom interferometers, atoms can be placed into superpositions of different paths and then recombined, allowing scientists to measure tiny effects from gravity, acceleration, rotation, and time. This is powerful because atoms are heavy enough to feel the influence of gravity in measurable ways, but still quantum enough to interfere. In a sense, atom interferometry lets researchers use the wave nature of matter as an extremely delicate ruler. The atoms do not simply behave like little balls flying along one track. Their quantum states can follow separated paths and later reveal the phase difference between those paths through interference. Even more striking are molecule interference experiments. Molecules are larger and more complicated than atoms, with many internal vibrations and rotations. One might expect their quantum behavior to disappear quickly. Yet researchers have shown interference with increasingly large molecules under carefully controlled conditions. Work associated with Marcus Arndt, Anton Zeilinger, and research groups in Vienna helped demonstrate that complex molecules can display wave-like interference. Some experiments have used large carbon-based molecules, including fullerenes, which are cage-like arrangements of carbon atoms. Later experiments moved toward even larger organic molecules containing many atoms. These objects are still incredibly small by everyday standards, but compared with a single electron, they are enormous little travelers. The challenge is decoherence. Larger molecules have more internal motion. They can absorb and emit radiation. They can collide with stray gas molecules. They can interact with the experimental apparatus. Every unwanted interaction risks leaking information into the environment and destroying the coherence needed for interference. To prevent this, experiments often use high vacuum, carefully controlled temperatures, narrow beams, and finely tuned gratings or laser pulses. The fact that interference can still be seen is astonishing. It shows that quantum superposition is not a special privilege granted only to photons and electrons. It belongs to matter more generally, as long as coherence can be preserved. Engineered quantum systems take this even further. In trapped ion experiments, individual charged atoms are held using electromagnetic fields and manipulated with lasers. Research groups at places such as the National Institute of Standards and Technology and the University of Innsbruck have used trapped ions to create precise superpositions of internal states and motion. These systems are important for quantum clocks, quantum simulation, and quantum computing research. Superconducting quantum circuits provide another major example. In these devices, electrical currents or energy states in tiny circuits can be placed into quantum superpositions. These circuits are not single particles in the old-fashioned sense. They are engineered systems involving many electrons acting collectively in a superconducting material. Companies and research groups connected with IBM Quantum, Google Quantum AI, and university laboratories use such circuits to build qubits and study quantum information. This sounds almost ordinary now, because the word qubit has become familiar, but it is deeply strange. A superconducting circuit is large compared with an atom. It is built by humans. It sits on a chip. Yet under extremely cold and carefully shielded conditions, it can behave according to quantum rules. It can occupy a superposition of two basis states, and that superposition can be controlled, measured, and used in computation. Optomechanical resonators explore another frontier. These are tiny mechanical systems such as vibrating membranes or beams coupled to light. Researchers are trying to place mechanical motion itself into quantum states, pushing superposition toward objects that look more like miniature machines than individual particles. The goal is to understand how far quantum behaviour can be extended and where decoherence becomes overwhelming. All these experiments share one lesson. The question is not simply how big something is. The question is how well it can be isolated, cooled, controlled, and protected from environmental information leaking away. Size matters, but so do temperature, complexity, internal motion, and interaction with the surroundings. This brings us back to the title. Quantum particles can be in two places at once, because their states can be coherently spread across alternatives. Larger systems can show similar behaviour when physicists work extremely hard to preserve that coherence. The boundary is not a brick wall between small and large. It is a gradual struggle between quantum possibility and environmental disturbance. Modern experiments with atoms, molecules, ions, superconducting circuits, and mechanical resonators show that superposition is real, testable, and not confined to imagination. Reality allows possibilities to overlap. It simply hides that fact very efficiently in the warm, noisy world we normally inhabit. Superposition is already strange when it belongs to one particle. A photon can be associated with two possible paths. An electron can have a wave function spread across more than one region. A quantum system can hold several possible outcomes together before measurement gives one result. But quantum mechanics has another kind of strangeness, closely related yet importantly different. It is called entanglement. Entanglement happens when two or more quantum systems share a single joint state, so that the properties of each part cannot be fully described on their own. Even if the particles later move far apart, the combined state may still connect the possible outcomes of measurements made on each particle. The particles do not merely carry separate hidden instruction cards. Their relationship is written into the shared quantum state. This can sound similar to a particle being in two places at once, but it is not the same idea. Spatial superposition concerns one particle or one quantum system being described across different possible positions or paths. Entanglement concerns two or more particles whose measurement outcomes are linked in a way that cannot be explained by treating them as fully independent classical objects. The confusion is understandable. Both ideas challenge the classical picture. In classical physics, an object is expected to have its own definite properties. One thing is here, another thing is there. Each can be described separately. If two objects are correlated, we usually assume they shared some ordinary past cause. Imagine putting one red marble and one blue marble into two boxes, then sending the boxes to opposite sides of the world. If someone opens one box and finds the red marble, they immediately know the other box contains the blue marble. Nothing mysterious has travelled between the boxes. The colours were fixed from the start. The measurements simply revealed what was already true. Albert Einstein, Boris Podolsky, and Nathan Rosen made a famous argument in 1935 that quantum mechanics seemed incomplete. Their paper, now known as the Einstein-Podolsky-Rosen argument, considered the strange correlations predicted by quantum theory. Einstein worried about what he called spooky action at a distance, because quantum mechanics seemed to imply that distant systems could be connected in a way that classical locality could not easily accept. For many years, this looked like a philosophical debate. Perhaps quantum mechanics was only an incomplete description, and perhaps some hidden variables secretly determined the outcomes all along. The particles might be like the red and blue marbles, carrying definite properties from the beginning. Then John Bell changed the question. In the 1960s, Bell developed a theorem showing that the debate could be tested experimentally. Bell's theorem revealed that no theory based on simple local hidden variables could reproduce all the predictions of quantum mechanics. If certain quantum correlations were observed, then the classical marble-like explanation would fail. Experiments later tested Bell's ideas. Alain Aspect and his colleagues performed influential tests in the early 1980s using entangled photons. Their results supported the quantum predictions. Later experiments became more refined, closing important loopholes. Research groups at Delft University of Technology, the National Institute of Standards and Technology, and the University of Vienna carried out major modern tests showing that quantum correlations violate Bell inequalities in ways consistent with entanglement. This does not mean entanglement allows faster than light communication. That point is essential. Entangled particles can show correlations stronger than classical local hidden variable theories allow, but they cannot be used to send a controllable message instantly across space. You cannot wiggle one particle in a laboratory and use the other as a tiny cosmic telephone. The universe is strange, but it has not accidentally invented free interstellar texting. The reason is that each local measurement still produces an outcome that appears random. Only when the two sets of results are later compared do the correlations become clear. That comparison still requires ordinary communication limited by the speed of light, so entanglement does not break relativity in the simple science fiction sense. It reveals that the quantum world cannot be understood as a collection of separate objects, each carrying its own complete list of pre-existing local properties. The whole state matters. This is where entanglement connects back to the title. A particle being in two places at once shows that one quantum system does not always have a single definite position before measurement. Entanglement shows that two separated systems do not always have fully independent definite properties before measurement. Both ideas undermine the classical assumption that reality is made from little objects carrying complete answers everywhere they go. There is also a deep connection between superposition and entanglement. In many experiments, entanglement is produced by creating a joint superposition involving several particles. For example, two photons may be created so that their polarizations are linked. Before measurement, the combined state contains several possible paired outcomes. When one photon is measured, the result is correlated with the result that will be found for the other. The state is not just one photon plus another photon, described separately. It is one shared quantum description. That shared description may stretch across large distances, even though it cannot be used to send messages faster than light. Entanglement is now a practical resource in quantum information science. It is studied in quantum computing, quantum cryptography, quantum teleportation, and quantum networks. Quantum teleportation, despite the dramatic name, does not move matter like a person stepping into a glowing machine. It transfers an unknown quantum state from one system to another, using entanglement and ordinary classical communication. The name is exciting. The laboratory reality is more precise and less likely to misplace your shoes. The difference between superposition and entanglement is worth holding clearly. Superposition says a quantum system can contain multiple possible outcomes at once. Entanglement says multiple quantum systems can share a combined state that cannot be reduced to independent parts. One is about alternatives within a state. The other is about relationships across systems. Both reveal that the quantum world is not built from simple classical certainty. A particle may not have one definite path before measurement. Two particles may not have separate definite properties before measurement. The deepest description belongs to the quantum state, and the quantum state can be spread across possibilities, particles, and space itself. So the mystery of being in two places at once is part of a larger lesson. Quantum reality is not always local, definite, and separable in the way everyday objects appear to be. At small scales, nature is woven from states, correlations, amplitudes, and measurements. And sometimes, the most important thing is not where one particle is, but how the possibilities of many particles quietly belong together. Quantum mechanics is not short of mysteries. It predicts experiments with extraordinary accuracy. It explains atoms, molecules, chemical bonding, lasers, transistors, magnetic resonance imaging, radioactive decay, and the strange behaviour of light and matter. As a practical scientific theory, it is one of the most successful frameworks ever created. And yet, after all that success, physicists still disagree about what quantum mechanics is telling us about reality. This is the territory of interpretations. The mathematics of quantum mechanics tells us how to calculate probabilities. It tells us how wave functions evolve. It tells us what results to expect when measurements are made. But the deeper question is what the wave function actually means. Is it a real physical thing? Is it a tool for calculating information? Does it collapse? Does it never collapse? Is a particle truly spread across space, or is something hidden beneath the formalism? These questions matter directly to the idea of a particle being in two places at once. The experiments show interference. The calculations require superposition. The wave function may describe more than one possible path or position. But what does that mean underneath? One of the most famous approaches is the Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg. This interpretation emphasizes that quantum mechanics gives predictions for measurement outcomes, and that we must be careful when applying ordinary classical language to unmeasured quantum systems. In this view, it is not always meaningful to say that a particle had a definite position before measurement, unless the experimental arrangement made that question physically answerable. The Copenhagen view does not treat quantum objects as tiny versions of everyday objects. It accepts that properties such as position, momentum, and path are tied to the way a system is measured. A particle may be described by a wave function containing several possibilities, and measurement gives one outcome. The exact meaning of collapse can vary depending on how the interpretation is presented, which is one reason the phrase Copenhagen interpretation can feel less like one tidy doctrine and more like a family of related ideas wearing similar coats. A very different approach is the many worlds interpretation, introduced by Hugh Everett in the 1950s. In this view, the wave function never collapses. Instead, all outcomes contained in the quantum state continue to exist as parts of a larger branching reality. When a measurement occurs, the observer becomes correlated with one outcome, while other outcomes continue in other branches. In many worlds, a particle in two places at once is not reduced to one place by a mysterious collapse. The full quantum state keeps evolving. The different possibilities become parts of separate branches that no longer interfere with one another once decoherence has done its work. This interpretation removes collapse from the theory, but it asks us to accept an enormous branching structure of reality. A bold trade, and not exactly a small one. Another interpretation comes from David Bohm's pilot wave theory, also called de Broglie-Bohm theory, because it develops ideas first explored by Louis de Broglie. In this view, particles do have definite positions at all times, but they're guided by a real wave. The wave evolves according to quantum rules and directs the motion of the particles. For the double slit experiment, pilot wave theory offers a striking picture. The electron goes through one slit as a particle, but the guiding wave passes through both slits and interferes with itself. That wave then guides where the electron can land. In this interpretation, the particle itself is not literally in two places at once, but the wave influencing it is spread across both paths. The price is that the theory is explicitly non-local, meaning distant parts of the guiding wave can matter in ways that do not fit simple classical locality. Then there are objective collapse theories. These suggest that collapse is a real physical process, not merely a change in knowledge or an apparent result of branching. One important example is the Girardi-Rimini-Weber theory, proposed in the 1980s. In this kind of view, quantum systems usually evolve according to the Schrödinger equation, but spontaneous collapses sometimes occur. For small systems, collapse is rare, so superpositions can persist. For large systems with many particles, collapses become overwhelmingly likely, making macroscopic superpositions disappear quickly. This approach tries to explain why electrons can show quantum superposition, while chairs, cats, and teapots do not appear in two places at once. It modifies the usual equation slightly, which means it may in principle be experimentally testable. That makes objective collapse theories especially interesting, because they try to turn a philosophical puzzle into a physical prediction. There are other approaches too. Some interpretations treat the wave function as representing knowledge or information rather than a direct physical object. Some emphasize the role of relations between systems, as in relational quantum mechanics. Some focus on consistent histories, where quantum events are discussed through sets of logically compatible histories, rather than a single classical timeline. Each approach tries to make sense of the same strange facts without changing the experimental success of the theory. The difficulty is that many interpretations give the same predictions for ordinary experiments. They agree about where the dots appear in a double-slit experiment. They agree about atomic spectra. They agree about quantum interference, tunneling, spin, and entanglement. They differ in the story they tell about what is happening beneath the calculations. This is why quantum interpretation remains unsettled. It is not because physicists are carelessly arguing over poetry while the laboratory waits outside with a clipboard. It is because the experiments force us into a world where classical assumptions no longer work, and the mathematics allows several deep ways of understanding that world. So what does it mean for a particle to be in two places at once? In a Copenhagen-like view, it may mean that before measurement, the particle does not possess one definite classical position, and the wave function gives the possible outcomes. In many worlds, it may mean that the full quantum state contains branches corresponding to different positions. In pilot wave theory, it may mean that the guiding wave occupies both paths, while the particle has one definite position. In objective collapse theories, it may mean that small systems can remain genuinely spread out until a physical collapse process selects one outcome. The experiments do not let us return to simple classical certainty. That door is closed. Interference patterns show that quantum alternatives are physically important. Bell tests show that local hidden variable pictures cannot explain all quantum correlations. Atomic structure shows that matter itself depends on quantum states, not little planets on classical tracks. But the final meaning of the wave function remains one of the great questions. Quantum theory tells us how to predict what we will observe. Interpretation asks what kind of reality makes those predictions true. The calmest answer is also the most honest. When we say a particle can be in two places at once, we are describing a real feature of quantum theory, superposition. What that superposition ultimately is depends on how one interprets the quantum state. But whatever interpretation we choose, the old picture of tiny objects simply carrying definite hidden positions through space is not enough. Reality at the quantum level is not less precise than we hoped. It is precise in a different language. The strangest ideas in physics often sound as though they belong only in thought experiments. A particle in two places at once. A photon taking more than one path. An atom described by a wavefunction spread across space. These ideas feel distant from ordinary life, as if they live only on chalkboards, in vacuum chambers, or in the part of a textbook where the diagrams become suspiciously abstract. But quantum superposition is not only a philosophical puzzle, it is also a working principle behind some of the most precise and powerful technologies humans have ever built. The clearest modern example is quantum computing. An ordinary computer uses bits. A bit is treated as having one of two possible values. It is one thing or the other. This simple idea, repeated billions of times, supports the digital world of phones, laptops, cameras, satellites, bank systems, streaming platforms, and the occasional printer that appears to have developed a personal grudge. A quantum computer uses quantum bits, usually called qubits. A qubit can be placed in a superposition of two basis states. That means its quantum state can contain both possibilities in a controlled combination before measurement. When measured, the qubit gives one outcome, but before measurement its state can be manipulated using the rules of quantum mechanics. This does not mean a quantum computer simply tries every answer at once in a magical shortcut. That popular explanation is too simple. Superposition alone is not enough. Quantum computing depends on superposition, interference, entanglement, and measurement working together. The aim is to arrange the quantum calculation so that wrong possibilities tend to cancel, and useful possibilities become more likely to appear in the final measurement. In that sense, quantum computers use the same deep feature seen in the double slit experiment. Quantum possibilities can interfere, they can reinforce or cancel. They are not ordinary guesses sitting politely beside one another, they are active parts of the calculation. Research groups and companies such as IBM Quantum, Google Quantum AI, IonQ, Quantinuum, and many university laboratories are trying to build and improve quantum processors. Some use superconducting circuits cooled to temperatures close to absolute zero. Some use trapped ions held in electromagnetic fields and controlled with lasers. Others explore neutral atoms, photons, or solid-state systems. Each approach has advantages and difficulties, but all of them rely on preserving fragile quantum states long enough to do something useful. The difficulty is decoherence. Qubits are delicate. If they interact too strongly with the environment, their superpositions lose coherence, and their quantum information becomes corrupted. This is why quantum computers require isolation, error correction, extreme cooling in some designs, and very careful control. A qubit is powerful not because it is large and dramatic, but because it is quiet, fragile, and very easily disturbed, rather like a deeply focused scientist, or a cat pretending not to hear its name. Superposition is also essential in quantum sensors. These devices use quantum states to measure tiny effects with extraordinary precision. Atom interferometers, for example, can place atoms into superpositions of different paths. When those paths are recombined, the interference pattern reveals small changes caused by gravity, acceleration, rotation, or time. This makes atom interferometry useful for studying gravitational fields, testing fundamental physics, and developing sensitive navigation systems. Because atoms have mass, their matter waves respond to gravity. Because they are quantum systems, their interference can reveal very small differences between paths. The particle-like atom becomes a measuring tool precisely because its wave-like state can be split and recombined. Atomic clocks are another example. Modern timekeeping depends on stable quantum transitions inside atoms. A cesium atomic clock, for instance, uses a precise transition between energy levels in cesium atoms to define the second. More advanced optical atomic clocks use ions or neutral atoms, with transitions at optical frequencies, allowing even greater precision. These clocks are not just impressive laboratory ornaments. They support global navigation satellite systems, telecommunications, scientific measurements, and tests of relativity. The fact that atoms have discrete energy levels and that quantum states can be controlled so precisely allows humans to measure time with astonishing accuracy. Quantum superposition also appears in magnetic resonance imaging, although the full technology involves many layers of physics. The spins of atomic nuclei, especially hydrogen nuclei in water and fat molecules, respond to magnetic fields and radio waves. Their quantum behaviour allows signals to be produced and detected, helping create detailed images of the inside of the human body. A deeply strange quantum property becomes a very practical medical tool. Lasers also depend on quantum physics. Atoms or other systems are prepared so that many particles can emit light in a coordinated way. The result is coherent light, with photons sharing a well-defined relationship. Lasers are used in fibre optic communication, surgery, manufacturing, barcode scanners, scientific instruments, and many other technologies. Their clean, controlled light comes from quantum rules about energy levels and emission. Even ordinary electronics owe much to quantum mechanics. Transistors rely on the quantum behaviour of electrons in semiconductors. The band structure of solids, the existence of conductors and insulators, and the behaviour of electrons in materials all depend on wave functions, the Pauli exclusion principle, and quantum states. The modern digital world is built from matter behaving in ways classical physics could never fully explain. So the idea that a particle can be in two places at once is not isolated from reality. It belongs to the same framework that explains atoms, chemistry, materials, clocks, lasers, sensors, computers, and medical imaging. The strange is not separate from the useful. In physics, the strange often becomes useful once it is understood well enough. The title's mystery therefore reaches far beyond the double-slit experiment. A particle in a spatial superposition reveals that nature allows quantum states to contain more than one possible path or position. A qubit uses the same broader principle to hold and process quantum information. An atom interferometer uses separated quantum paths as a sensitive measuring device. An atomic clock uses stable quantum transitions to keep time. A laser uses controlled quantum emission to produce coherent light. Again and again, the lesson is the same. Quantum mechanics does not merely describe a weird hidden layer beneath the world. It quietly supports the world we have built on top of it. When quantum particles behave as though more than one possibility is real before measurement, they are not breaking the rules. They are following the rules that exist beneath ordinary experience. The challenge for technology is to protect those delicate rules from noise, heat, and environmental disturbance long enough to use them. That is what modern quantum science is learning to do. It takes the fragile language of superposition and turns it into clocks, sensors, computers, secure communication, and new ways of probing nature. A particle being in two places at once may sound like the beginning of a paradox. But in the laboratory, it can also be the beginning of a measurement, a calculation, or a technology. The same quiet mystery that unsettles common sense has become one of the most practical truths in modern science. So why can quantum particles be in two places at once? The safest answer is that, at the smallest scales, a particle is not always described as a tiny object sitting at one definite point before anyone measures it. It is described by a quantum state, and that quantum state can include more than one possible position, more than one possible path, or more than one possible outcome at the same time. That is the careful meaning behind the strange phrase. A particle is not usually being copied like a miniature object duplicated across space. An electron is not splitting into two little half-electrons, each politely taking a different doorway. A photon is not wearing a tiny disguise and sneaking through both slits like a very committed stage magician. Instead, the particle's wave function can be spread across alternatives, and those alternatives can remain part of one coherent quantum state. The evidence for this is not just philosophical, It appears in experiments. In the double-slit experiment, electrons or photons can be sent toward two openings one at a time. Each particle is detected as a single event, one dot on a screen. Yet after many particles arrive, an interference pattern appears. That pattern is the clue. It shows that the different possible paths were not merely unknown options. They were physically relevant parts of the quantum description. The path through one slit and the path through the other slit could combine, reinforce and cancel, shaping the final pattern. That is very different from ordinary probability. If a coin is hidden under one of two cups, the possibilities do not interfere. The coin is simply under one cup, whether we know which cup or not. But in quantum mechanics, probability comes from probability amplitudes. Those amplitudes can add together or cancel out. They give possibility a structure that ordinary guesswork does not have. This is why quantum theory replaced the old picture of particles as little classical dots with fixed hidden paths. Max Planck opened the door by showing that energy exchange could come in discrete packets. Albert Einstein showed that light could behave as photons. Louis de Broglie proposed that matter itself had wave-like properties. Clinton Davison, Lester Germer, and George Paget Thompson helped confirm that electrons could diffract like waves. Erwin Schrödinger gave physics the wave function, and Max Born connected it to probability. Werner Heisenberg showed that properties like position and momentum cannot always be pinned down with unlimited precision. Step by step, the old certainty softened. The quantum world did not become vague because scientists became careless. It became precise in a new way. The precision moved from definite classical paths to wave functions, amplitudes, probabilities, and measurement outcomes. Quantum mechanics does not always tell us that a particle had one hidden position all along. It tells us how the quantum state evolves, how possibilities combine, and what probabilities we should expect when a measurement is made. Measurement is where the story narrows. Before measurement, a particle's state may be spread across more than one possible place. During measurement, one definite result appears. The electron is found here. The photon strikes there. The detector clicks once. The world gives a single answer. But the pattern of many answers reveals what came before. Interference shows that the particle's earlier state was not simply classical ignorance. It was a coherent superposition. This also explains why we do not see chairs, planets, cups, or people in obvious superpositions of different places. Large objects are constantly interacting with their environments. Air molecules strike them. Light scatters from them. Heat radiation flows in and out. Their atoms vibrate. Information about their position leaks into the world around them almost instantly. This process is called decoherence. It does not make quantum mechanics disappear. It hides the visible effects of superposition by preventing alternatives from interfering. Heinz, Dieter Zeh, and Wojciech Zurek helped develop this idea, showing how the classical-looking world can emerge from quantum foundations through environmental interaction. So the reason ordinary objects appear definite is not that they are made from non-quantum ingredients. They are made from quantum ingredients. But they are large, warm, complex, and deeply connected to their surroundings. Their delicate alternatives lose coherence far too quickly for us to see them behave like isolated quantum particles. Even so, scientists have pushed quantum behaviour into larger and larger systems. Neutron interferometry, atom interferometry, molecule interference experiments, trapped ions, superconducting circuits, and optomechanical systems all show that superposition is not merely a poetic idea. With enough isolation, cooling, and control, quantum states can be split, preserved, recombined, and measured. This same principle now sits behind modern quantum technology. Qubits rely on superposition. Quantum sensors use matter waves to detect tiny changes in gravity, acceleration, rotation, and time. Atomic clocks depend on precise quantum transitions. Lasers, semiconductors, magnetic resonance imaging, and much of modern electronics all depend on the deeper quantum structure of matter. The strange is not separate from the useful. The weirdness is part of the machinery. So when we say quantum particles can be in two places at once, we are using everyday language for a deeper scientific fact. A quantum particle can exist in a spatial superposition, where more than one possible location remains part of the same coherent state before measurement. Those possibilities can interfere. They can shape what is later observed. And when measurement happens, one outcome becomes real to the detector, while the wider pattern still carries the signature of the possibilities that were there before. That is the quiet wonder of quantum physics. Reality is not less lawful than we imagined. It is not messy, magical, or undecided in a careless way. It follows rules of extraordinary precision. But those rules are not the rules our everyday senses evolved to expect. At the smallest scales, nature does not always begin with one definite path, one definite position, and one tidy little answer waiting patiently behind the curtain. Sometimes, before the world gives a single result, possibility itself is part of reality. And in that carefully measured, experimentally tested sense, a quantum particle really can be in two places at once,